Hello? Yes. The next presentation is by Xiangjun Xing from Shanghai Jiao Tong University, Fluctuations and Nonlinear Elasticity of Ideal Nematic Elastomers.
So I want to thank the organizers of this wonderful workshop to invite me to give a talk on this subject related to nematic elastomers. So I hope that I could give newer results. Right? I was still thinking about that 1 week ago, but I couldn't do it because I'm afraid my new results are still incomplete and way too messy. Okay? So I have to go back to my older stuff, which I have done like probably 10 years ago. Okay? So the talk is a ideal nematic elastomer. Ideal could mean anything but realistic. So first, let me acknowledge my collaborators in this topic. Leo Radzychowski, my PhD advisor, and Tom Lubinsky, which I had the luck to work with in my early stage of research. So I also interact with a number of other people about this topic, like John Toner, Paul Goldbart, Steno, Mukhopadhyay, Mark Warner. So my talk will have 3 parts. So in the first part, I will discuss a general method of constructing strength tensors for systems with partial translational orders. Okay. In the second part, I will study this description of strengths for nematic elastomers. In third part, I will discuss the role of fluctuations on the macroscopic elasticity of nematic elastomers, ideal nematic elastomers. Okay. So let's start with elasticity theory of a conventional solid. So a solid is defined as an array of atoms interacting with each other via some potential energy. Okay? So they have some fixed equilibrium configuration where their energy is minimum. And so when we deform a solid, we change the distance between atoms. So therefore, the deformation costs energy. So that's the main, the basic aspect of elasticity. So let's consider 2 points separated by dx in the undeformed reference state. Okay? So we apply a deformation, which is described by a linear transformation. Okay? So this lambda is a 3 by 3 matrix. And the displacement between these 2 points in the deformed state is given by dr, which is related to dx by a linear transformation lambda. Okay. So here x is usually called the Lagrange coordinate, and r is called the Eulerian coordinate. It is the coordinate of a mass point in a deformed state using a fixed coordinate system. So the distance between 2 points in the deformed state can be expressed in terms of dx using a quadratic forms. Okay? We just take the inner product of dr with itself, and you find that the matrix between 2 dx is given by lambda transpose times lambda. So this matrix or tensor has a special name. It's called the Wright-Cauchy-Green deformation tensor, or some people call it metric tensor, because it is the stuff we use to calculate the distance in the deformed state. So we call C or G, whatever it is, it's a lambda transpose times lambda. And it's a very important object in elasticity theory. So this. Oh. Okay, so now let's calculate the change of distance between 2 points. Okay, in the in the deformed state and in the undeformed state. So this change of distance can be expressed as a quadratic form like this. So the matrix is C minus 1. Okay, and we define this matrix divided by 2 to be the Lagrangian strand tensor. Okay, and we can write them out. Their components. So EAB is given by the partial derivative of R vector with respect to XA, dot product with the partial derivative of R vector with the XB. So and we can define the a phonon field U, which is the change of the position of the mass point. Okay. And we can express the Lagrangian strand tensor in terms of the partial derivatives of the phonon field. So we see a linear part, okay? So DAUB plus DBUA plus a nonlinear part. And it's important to notice that in the nonlinear part, the component, the index of a U field is always traced over, okay? This is because when we're constructing this nonlinear strand tensor, vector R dot into vector R, it's always a inner product. So we can express the change of distance into this in terms of this strand tensor. Okay, and there's another way to define strand tensors. We can express dx vector in terms of dr. Okay, so we use dr as the basic degree of freedom, basic variables. Then the change of distance can be written into dr dot some matrix dot dr. And this matrix is called the Eulerian strand tensor. Okay? It's 1 minus lambda my inverse transpose times lambda inverse divided by 2. Okay? And we can express the little e, okay, Eulerian strand tensor in components like this. So now I found there's a mistake here. Okay? The sign is negative. Okay, the nonlinear part. Okay, but again, we have to notice that vector u dot into vector u. Okay, so the index of u is always traced over. So this is important. So this is a elasticity theory for a conventional solid. So even though it's complicated, but it's not really. Most of the time, we don't really use it, because for most conventional solid, linear elasticity is sufficient. Displacement field is never big. So we don't have to bother with all these complicated nonlinear parts. But there are many systems that we know that for which nonlinear part is important. So these are the soft matter systems we study most. Right? These systems typically have partial translation orders. They are not three-dimensional solid. They only have solid-like rigidity along certain fewer directions. Okay, so for these systems, nonlinearities and the fluctuations are important. So we do have to take care of the nonlinearity of the elasticity correctly. So let me give you 4 examples. Right, this is an elastic rod. It's a one-dimensional solid embedded into a three-dimensional space. Okay, and we can also have a two-dimensional crystal or solid embedded into a three-dimensional space. Okay, so these systems, because of their reduced dimensionality, okay, they have a much bigger room to fluctuate in three-dimensional space. Okay. And we also have liquid crystals. Okay, SMEC liquid crystal, which is essentially a stack of parallel liquid membranes. Okay, if you zoom in microscopically, then each fluid sheet is made of rod-like molecules. Okay, in the simplest SMEC system, these molecules are standing up; they are perpendicular to the plane. Okay, and we also have a columnar phase, where which is essentially an array of parallel liquid lines. So one-dimensional liquid stacked to each other. Okay? And if you zoom in, each line is made of disk-like molecules. So these systems, they have a very different nonlinear elasticities. So we will have to do them correctly. And there are more complicated systems, right? You can imagine, like, what if a rod is bended into a helix, okay? Or we know that there are a lot more exotic symmetrics with richer inner structures. So it is also a problem how to work out the nonlinear elasticity of these systems. So so in some sense, all these problems have been worked out a long time ago, using different methods. So what I'm doing now is try to give a unified method to do all these problems, which I believe is simpler. So constructing a proper nonlinear strength tensor is the first step toward understanding of the nonlinear elasticity of these systems. So why bother nonlinear elasticity, right? So let me give you two aspects of these systems. So the first aspect is what we call anomalous elasticity. So we know that there are a class of systems, including symmetric liquid crystal, columnar liquid crystal, crystal membranes in three-dimensional space, and ideal nematic elastomer, and some other systems. So they show very, very bizarre properties at finite temperature. So one of them is a strictly nonlinear stress-strain law, even for infinitesimal deformations. Okay? And some of the systems also show universal Poisson ratio. So the ratio between certain pair of elastic moduli is a universal number. It's independent of microscopic details. And they also show singular phonon correlation functions. Okay? The correlation function is not an analytic function. So these systems have been studied in great detail by these people, Lubinsky, Toner, and Razhovsky. So I basically, during my PhD life, I learned about this stuff from these people. So the second example, which I did myself with collaborators, is the correction of the elasticity of isotropic rubbers due to long wavelength fluctuations. So in this system, so there's no anomalous elasticity like the first class. Okay, so for infinitesimal deformation, this elasticity is linear, there's no problem. But if you look at the large deformation behavior, then there's a large corrections to the elasticity due to these long wavelength fluctuations. So this is a result which we plotted in our paper. So basically here, this is a vertical axis is the Mooney stress of an isotropic rubber. Okay? So according to classical theory of a rubber elasticity, it is a flat straight line. Okay? Now this data is taken from some very old work, and it shows some peak. Okay? So this peak is universally exhibited by many, many isotropic rubbers. And so our theory basically takes into account these long wavelength fluctuations in the presence of large deformations. Okay? We calculate the correction up to one loop, and we obtain some correction to the free energy, and we plot the result. So this is our result. Okay? Basically, there's no free parameters in this fitting. So everything is fixed. So to understand the nonlinear elasticity of these soft matter systems, we need to do the following steps. So the first step is to have a correct nonlinear elastic Hamiltonian, okay, to capture the right physics, to have the right nonlinearity. Okay? This step is not the most difficult step, but it's still non-trivial. Right? So we need to have a proper description of a strand deformation. So this is where geometry matters. Okay? Then we need to construct the proper linear strand tensors, nonlinear strand tensors. And then we have to construct an elastic free energy as a function of a nonlinear strand. So this is more or less easy. And the second major step is to include long wavelength fluctuations into the elasticity theory. So basically, we have to do a statistical field theory. We have to put statistical mechanics and elasticity together. In some time, for some systems, we have to do renormalization group transformation. So let me start with a simplest example, elastic rod. Okay, so we have a rod. Okay, the ground state is straight, and let's set up a system, the coordinate system, such that the axis is parallel to the x-axis, for example. Okay, so this is our reference state, and let's consider arbitrarily deformed state, where this rod is no longer straight. Okay, so let's look at a small segment, the dx, in the undeformed state. Okay, after the deformation, it's transformed into dr, okay, which is a linear transformation of dx. Okay, via this lambda, 3 by 3 gradient, deformation gradient. Okay, so now the elastic energy must be a function of the change of distance. Right, this is essentially solid. So distance between mass points determines the elastic energy. So let's express this change of distance. Again, we know that it can be expressed in terms of Lagrange strength tensor, which is C minus 1 divided by 2. Okay. So now let's introduce the parameterization of this vector R in terms of x. So x is really one-dimensional. Okay. So we need to introduce two variables. One is u. U is the stretch or compression of the rod along its axis. Okay. And we have a two-dimensional field h, which is the undulation, is the transverse displacement of the rod. Okay. If we plug this parameterization into the strength tensor, we find this following expression, nonlinear expression. Okay. So it's du dx plus half of du dx squared plus half of d h dx squared. So it's well known that this is the right nonlinear strength for elastic rod. Okay. So slightly more complicated example is a polymerized membrane, crystal membrane. Okay, whatever. It's a two-dimensional solid embedded into a three-dimensional space. Okay. So let's choose the coordinate system such that the normal of this sheet, the membrane, is along z-axis. Okay. So this is the reference state. Then in the deformed state, so the membrane is tilted and deformed. Okay. So what's shown here is not the whole membrane. It's really a small part of the membrane, okay, which can be treated as flat even in the deformed state. So now in the deformed state, the vector, normal vector, is little n. Okay, used to be z. We also call it capital N. Okay, in the undeformed state. Okay, and both the x-axis and the y-axis are also deformed. So we can also calculate the change of distance between two mass points. Okay, so this dr squared minus dx squared. Again, it can be expressed in terms of E, which is the Lagrange strength tensor. Okay, so now the parameterization of R vector is such that U vector is a two-dimensional, and H, the undulation, is only one-dimensional. Okay, you put this back in, you find you have, of course, you have this. Okay, this is the Lagrange strength tensor confined, restricted onto xy plane. Okay, this is also well known. It's correct. Okay. Okay. Almost trivial, right? So now let's look at first, I think, a somewhat non-trivial example. So let's look at the symmetric liquid crystal. It's a stack of parallel fluid membranes. Okay? In the ground state, it's the normal of these membranes are along z directions. And in the deformed state, it's along some other direction, little n. Okay? So now, when we deform the system, so the deformation of this three-dimensional system can always be described by a 3 by 3 deformation gradient, right? It's a three-dimensional system, so lambda should always work. But what we care is the new normal, okay? The normal of the membranes in the deformed state. So it's a elementary problem in geometry to work out this normal, how the normal vector transform. Okay, It's given by lambda not inverse transpose dot into capital N, the original normal, and properly normalized. Okay. So now the distance between the different sheets, neighboring sheets of membranes in the deformed state can also be calculated. Okay. Once you know the normal, you can calculate the distance. You just have to project, a vector, deformed vector, back onto the new normal. Okay. You find out the d naught, okay, the new distance, which is given by d naught divided by square root of a certain this particular bilinear form. Okay. So be careful here because the matrix appearing inside the bilinear form is lambda inverse times lambda inverse transpose. Okay, this is neither Lagrangian strand tensor nor Eulerian strand tensor. That's a different object. Okay, so the proper nonlinear strain must be given in terms of this particular matrix, right? So this is given by identity matrix minus this matrix, okay, divided by 2, and only the component of this matrix along z-axis matters. So we have to take the ZZ component. So now we take a parameterization of the deformation, okay, 3-dimensional phonon field, and we plug it back into here, into this part, and we found that it's given by dzu minus half of a gradient u squared. So this u is actually uz. It's a z component. So notice that ux and uy do not appear. This means that we are doing correct, right? If we do it incorrectly, we will end up with ux and uy in the nonlinear strand, and we don't know how to proceed anymore. So the essential step is to do the right projection, to do the projection to get the normal distance in the deformed state. So this is a slide which shows the little details of calculation. So let's look at columnar electric crystal phase, okay, which is a 2-dimensional array of parallel fluid lines. Okay, so here the energy, the elastic energy, is a distance of is a function of the distance between neighboring parallel fluid lines. So we have to calculate this distance in the deformed state. So the calculation is a lot similar. It's quite similar, right? It's d naught in the undeformed state. It's d in the deformed state, and then we have to work out how this, the vector between two lines change, and then we have to subtract off the longitudinal components. And if we do that, we'll find that d changes as this. Again, it's inverse of this right Cauchy-Green strand tensor, which is the same thing as appeared in the SMEC systems. Okay. So now the proper nonlinear strain is given by, again, the same thing. It's a half of identity minus C inverse. Okay. Now if we insert the parameterization of phonon fields, and we get this nonlinear strain. Okay. Here, Uij are restricted to 1, 2, or x and y, restrict onto the perpendicular plane. Okay. So only 2 components of phonon field appear. Not UZ, okay. If we get UZ, then we did it wrong. So we can proceed to apply this method to more complicated systems. Like, what if you have an elastic rod, but it has a finite thickness, so it can have torsion, right? What if this rod is banded into a helix, and we have some other soft deformation comes in, or some exotic SMEC, or maybe you have a membrane which has some internal orientational order, right? So all these things can be worked out, but I'm not going to show the result to you here. So I'll move on to the second part of the talk. Okay, so I have to speed up a little bit. So now there's a nematic elastomers. Okay, So this is the stuff I did a long time ago. Basically, it's my PhD thesis. So we published, one PRL and one Europhysics letter, and on 03, I think. Yes. And 4 years later, I published a long paper, 98 pages, with Leo Razovsky, okay, in Annals of Physics. So this paper took me about 5 years to write. And Lubansky and his postdoc published EPL back-to-back with our paper in 03. And they published a long paper much earlier, okay, in 04, right? Many results discussed, in these two bunch of works are similar. Okay. So let's start with the spontaneous shear deformation, right? So there have already been several talks on this, on nematic elastomers. So I believe, you already have a rough idea for what soft mode is. So basically, nematic elastomer is a kind of a system, a three-dimensional solid, which spontaneously develops nematic order, okay, even though it's a solid. So let's start from an isotropic state. So this IRS is not internal revenue service. It's an isotropic reference state. And start from this state, you develop a nematic order. Okay, and because of the coupling between elasticity and the nematic order, the system deforms along the direction of nematic order. Okay, so this is let's call the NIS as a nematic reference state. So because of the the direction is randomly chosen, right? Because of the symmetry, rotational symmetry of the isotropic state. So you can equally well choose rotate the isotropic state first by an orthogonal matrix O, and then develop nematic order in a different state, a different direction, N, okay? And accordingly, the solid will also be deformed in a different direction. So this lambda N is different from lambda N naught. They differ by a similarity transformation. Okay. So now suppose you go from this nematic reference state to this different nematic state. And by symmetry, they should cause the same elastic energy. Okay. And these two states, they are related by a rotation of the nematic order, of course, together with a non-trivial shear deformation. So this is not a simple rotation of the solid. It's a shear deformation. So it is a shear deformation together with a rotation of the nematic director that causes zero energy. So this is the soft mode, which was the first discovered by Golubovich and Lubansky in 1989. Okay, so this paper has become a classic in this field. So now we will try to express the deformation gradient of this soft deformation. Okay, so this R is the coordinate, Eulerian coordinate in this deformed nematic state, and this X is the coordinate of this nematic reference state. So we want to work out this deformation gradient. And this thing, little lambda, can be expressed in terms of this big lambda, which is the deformation gradient defined relative to this original isotropic state, together with this lambda naught, lambda n naught, which is the spontaneous deformation from the isotropic state to the nematic reference state. Okay? So we have an expression for this soft deformation. Okay? So now, if we construct the free energy correctly, then it must satisfy certain symmetries. Right? First is the global rotational symmetry in the current state, in the deformed state, I mean, and also in the initial state. So the elastic energy can assume uniform deformation. Okay, is a function of n naught, n directors in the undeformed and deformed state, and this deformation gradient. Okay, so if we rotate both states properly, we get the same free energy, and it should also be invariant under soft deformations. Okay, so if you take a ground state, you do a soft deformation, the free energy is 0. One step further, okay? If we take a system, you apply soft deformation, and you apply another arbitrary deformation. Okay? Free energy should be the same as if you do not apply the soft deformation in the beginning. Just directly apply the non-soft deformation. So this is also a symmetry. Right? So let's define these two step length tensors here. Okay? So basic step length tensors is the square of the spontaneous deformation, okay, for given director, nematic director. So the first example of free energy, nematic elastomer, free energy, which satisfy all these symmetry properties, is given by that of Warner and Terenger. So they construct this very simple free energy, okay, which is a simple generalization of a classical rubber elasticity. Okay. If you take L naught and L both to be identity, then this free energy reduced to that of a isotropic rubber. Okay. But this theory also has an additional symmetry, which is not required by physics. Basically, if you start with first you deform the system, okay, non-soft deformation. Then you apply a soft deformation. Okay? It says that the soft deformation does not change the free energy. But this is not required by any physical principles. Symmetry only says that if we apply soft deformation, okay, then you do something else. It's as if you didn't do the soft deformation. Okay? But not vice versa. If you do deformation first, then do another soft deformation, it may not keep the free energy same. So we construct an invariant nonlinear strength tensor. Okay, so this is basically a rewriting of this tensor in the new classical theory. Okay, we just move, shuffle things around. Okay, and it's by definition it's symmetric. So note that L naught, the director inside L naught, is the director in the initial state, nematic reference state. Okay, it's traced over. So this strength tensor automatically vanishes for soft deformations. Okay, and in isotropic limit, it reduces to the left Cauchy-Green strength tensor. And under rotation in the final state, in the current state, okay, it's transformed as an ordinary second rank tensor. Okay, so this is a cartoon which shows why the strength is good, because this strength tensor can be written in terms of the gradients, deformation gradients, which are relative to the isotropic reference state. So it does not even mention the nematic reference state. So by construction, this tensor is a description of the distance from this ground state manifold to the current state. So it is an invariant property. That's why it encodes the isotropic, encodes the soft mode. So let's take this strength tensor and decompose it into different components, right? So let's choose N to be the director in the deformed state. Okay, so we can decompose this into the 4 parts, right? You have a VNN, projection of V onto the director, okay? And this is a scalar, and we have a transverse mixed part VN perp, which is a vector, has 2 components in 3-dimensional space. Okay, we have V perp, which is a 2x2 matrix. Okay, and we can further define new components, which is trace of V. Okay, that's a linear combination of VNN and the trace of V perp. Okay, plus V tilde. V tilde is a combination of VNN and V perp. Okay, it's a contraction of this traceless part of V and together with the matrix. Okay, this J, and we have still have 2 parts left in V perp. Okay, let's call this V perp tilde, which is a traceless part inside the perpendicular plane. Okay, and the trace V perp, not trace V perp. No, and this part, the mixed part. Okay, VN perp. So we can express the free energy as a function, as a quadratic function of this nonlinear strength tensors. Okay. into these components. Okay, so this trace V has a physical meaning. This is isotropic change of volume. So this is a Buck mode. The corresponding modulus is the Buck modulus. And then we have C. Let's forget C for now. Okay, let's look at this mu L. Okay, V tilde NN is the stretch along the director and the shrink in the perpendicular plane, isotropic shrink in the perpendicular plane. So it's what we call a longitudinal shear. Okay, it preserves the volume. So its modulus is called V mu L. And we have this transverse shear, which is a shear deformation confined in the perpendicular plane. So that's the V tilde perp. And the corresponding shear modulus is mu. Okay. And we have this mixed mode. This is the soft mode. Okay, it has a combination of a shear deformation together with the rotation of the director. And so this is our elastic free energy, right? And let's look at the mixed soft mode. Okay, VNI, basically we find it's a linear combination of linear strain and the rotation of the director. Okay. So now this is similar to a conventional uniaxial solid. Okay. In uniaxial solid, okay, it's a free energy, elastic free energy. It also has 5 elastic constants. Okay. But of course, the strains only involve elastic deformations, but not rotation of directors. There's no flexible, no directors in uniaxial solid. Okay, no mobile directors. Okay. And to get the full free energy, of course, we still have to add the Frank free energy, which penalizes the deformation of directors. Okay. So now if we take the free energy, okay, we ignore all the high order terms, we only keep quadratic terms, and we get this result. Here E epsilon is a linear strength tensor. Okay, so now we can integrate out the director fluctuations. Then this term will be gone. Okay. The mu tilde n perp will be gone. Okay. And if we compare the resulting theory with a uniaxial solid, then you see that C5 would vanish. Okay? It looks like you have one missing shear modulus. So this is what Glubovich and Lubinsky said in their classical paper. So it's a solid, it's a uniaxial solid that has one missing modulus. So now we want to study the effect of fluctuations. Okay? So we want to do statistical mechanics. There are different ways of doing it, right? So we can choose different statistical ensembles. We can either do strain ensemble, where we impose a macroscopic deformation. That's a little lambda naught. This is the background deformation you can control externally. And you let the system also have a local fluctuations U field, and you have to do this partition functions. You have to sum over all configurations of U and the director. Okay, local fluctuations. Okay. So often we have to impose proper boundary conditions on this U field and delta N. And if we are lucky, the boundary condition does not matter if we only want to calculate Buck properties. But this may not always be the case. It can be wrong. We can also do stress ensembles. Okay? We can introduce a constant force acting on the surface of the system. Okay? This is equivalent to a linear part in the elastic Hamiltonian. Okay? And you put this in, you have to do this the partition function again. Okay? And you can show that this resulting thermodynamic potential is the Legendre transform of the elastic free energy, which we can calculate in the strain ensemble. Okay. So all these are standard results in physics. So let's apply these in the machinery of statistical mechanics to this problem. Okay. So we have this elastic Hamiltonian, and we want to integrate out director field. So to simplify the problem, okay, otherwise the partition function is way too difficult to calculate. 2 minutes. Okay, good. Yeah. So after we doing that, we end up with the 4 elastic modulus plus 1 Bragg constant. Okay. And we found that the appropriate nonlinear strength tensor is this part. It looks like this. Okay. So only the only relevant nonlinearity is that of UZ field. Okay. And to simplify this expression, we further rescale the photon fields so that this alpha, nasty factor alpha, goes away. It becomes 1. Okay. Okay. So we do the harmonic theory. We look at the harmonic fluctuation of the U field. We found that it's a variance actually diverges at finite temperature. So it diverges the same way as that of symmetric liquid crystal. Right? So then we do, some rescaling transformation on the theory, and we found that if we will rescale all the variables properly, then we find that it's equivalent to a rescaling of temperature. So below 3 dimensions, the temperature becomes larger and larger as we look at the larger and longer scales. This means that below 3-dimensional space, including 3-dimensional space, long wavelength fluctuations are important. So we have to do renormalization group to take into account these fluctuations. So this is what we do, right? So we integrate out modes of large momentum or short scales perturbatively and recursively. Okay? And we obtain recursive relations for all these elastic constants. So this is the only relevant Feynman diagrams. Okay? So the resulting flow equations for all the parameters are like this, right? Looks not too bad. But it's not good because the renormalization is not multiplicative. Okay? Which means that we are not using the right set of parameters. Right? So we have to find the right set of parameters. Are those we discussed earlier. It's P Buck modulus, longitudinal shear, transverse shear, Frank constant, and this cross coupling. So these parameters transform multiplicatively. Okay? And we work out all these flow equations for these parameters. GL and Gperb, again, they are dimensionless ratios. So the flow equation for GL and Gperb are really horrendous. Okay? And you have another two-dimensionless parameters, x and y, okay, which is somewhat simpler. Okay. So I work out, basically, it took me 2 years to work out the flow equations and understand the consequence. So this is the details. And we found that these eta exponent, which is the anomalous exponent for these elastic constants. Okay. And we found that there's a universal ratio between Gperb and the GL. So GL divided by Gperb is basically half, the fixed point value. Okay. So the implications of these RG results are following: that all the shear moduli vanish in long scale limit, but the Buck modulus remains finite. Okay. The splay constant actually diverges in the long wavelength limit. Okay. And there's a universal Poisson ratio between mu L and mu, okay, 2 shear moduli. Okay. And we also calculate the crossover length scale, okay, which depend exponentially on temperature. So this range, possible range of this scale is huge. So we have not much to say about whether they are experimentally measurable or not. It depends on the concrete systems, I think. So this is the conclusion. So I have talked about a proper description of deformations for soft matter systems and have applied this strategy to nematic elastomers. And I have talked about statistical mechanics of these and the nonlinear elasticity of these nematic elastomers. Okay? So in general, developing elasticity theory for soft matter system is difficult. That's what I have learned. but they are also interesting. Thank you for your attention.
Thank you very much. I'm afraid that we are a bit late, so we have to move to the next presentation, and maybe we can, people who are interested in asking questions can do that during the photograph session. Don't forget